as we continue our study of greedy algorithms, we would not be doing anybody any services if we ignored Prim's algorithm and Kruskal's algorithm. So Prim and Kruskal are two algorithms to solve the same problem, right? To solve the minimum spanning tree problem, which is a problem in graphs. And they're both surprising for the same reason. Essentially, by now in the class, you should have been convinced that greedy algorithms are unlikely, in general, to be optimal algorithms to solve anything, right? They may be fast, but they're not likely to be able to solve a problem correctly in a reliable way. And you should have been convinced that graph problems may be challenging, right? Graph problems may not even have efficient algorithms. So Prim and Kruskal are two separate, completely different algorithms for solving the same graph problem, and they both do it efficiently, and they both do it correctly. So they're quite surprising in this way, and it suggests that maybe the problem that we call the minimum spanning tree problem has some fundamental properties that make it easy to solve. So here's how I like to motivate this. So suppose I'm building a house, and I have a floor plan, and I have to decide how to run wire. Okay, so for example, maybe I want to wire the house up with Ethernet so that I have an Ethernet port in each room. How do I run the wires to minimize the total amount of wire? Right? So how to run my Cat5 cable, my Ethernet cable. Right? So here's a way to think about this. So let's think of the floor plan as being like this. And there's some rooms. I don't know. I'm not an architect, so I don't know what a room's supposed to look like. Anyway, there's a floor plan of a house. And let's say my service entrance is here. So that's where, Comcast came and drilled a hole, and that's where I'm going to stick the router. So now I got to figure out how do I want to run my Ethernet cable to each of the places where I want to have a jack. I want this house to be super connected to minimize the total amount of cable, right? So I want to not just connect to every single one of these jacks, but I also don't want to spend too much on cable. So I have to have two properties, right? Connect to every jack, right? Each of these, and minimize total cable length. Right? So this is now, I would argue, this is a different question than the question that Dijkstra's algorithm would like you to answer. So Dijkstra's algorithm would say, let's imagine that each one of these runs of cable is a single cable. And so for each one of these jacks, I want to have the shortest possible routing from that jack to the router. Right? That's the question that Dijkstra's algorithm is asking. Prim and Kruskal, on the other hand, are not asking that question. They're looking for something called a minimum spanning tree. So they're looking for the question, they're asking the question, not how do I minimize path lengths, but how do I minimize total cable? So rather than saying I want to have a short path from the router to every single one of my jacks, they're saying I don't care how long the path is, I just want to make sure that I don't waste money on cable. Right? All I care about is that these are connected. The house isn't big enough for the length of cable to slow me down in an appreciable way, right? I'm not doing high frequency trading or something like that. So all I want to do is just make sure that I minimize the total amount of cable. And there's a lot of ways I could do it, right? I could run cable like this, or maybe I could run cable like, I could run something across like that. And there's a bunch of different ways of connecting all this stuff together. And so the way that I might approach this in terms of these algorithms is I might model this as a graph. And I could think of each edge in the graph as a possible routing of cable. So what I could do is I could take this floor plan, model it as a graph, essentially model the possible routings as a graph. And so then I'd get something like this, right? Each jack, where I might want to have an RJ45 connector, would be a dot, and I just want to say, well, I could run cable like this. I could run it like this. I could run this. I could run under the floor. I could do all this stuff. There's all these different ways I could run cable, And then I would assign a weight to each of these, and the weight of each of the edges might be like the length of that edge in the actual floor plan. So maybe I've got some 8s, maybe I've got some 4s, you know, this is not to scale. Maybe these are super narrow rooms, whatever. I model the possible routings as a weighted graph, and then my goal is to find a subset of edges that accomplishes two things, right? That accomplishes this thing, connect to each one of the jacks or the vertices, and 2, minimizes the total cable length, right? What does that mean? Well, it would mean to minimize the total distance included in my subset of edges, okay? So this is called, a graph that satisfies those two things is called a minimum spanning tree, okay? So our goal is find a minimum spanning tree of this graph. Okay, so we talked a little bit about spanning trees when we did Dijkstra's algorithm, but let's make sure that the definition of a minimum spanning tree is clear. All right, so I'm going to rephrase the definition of a spanning tree just a little bit from last time. So we've got this definition that says, suppose I've got a graph G, then a spanning tree of that graph, of this graph G being a set of vertices and a set of edges, is another graph, and I'll write it like this. So it's a graph GST, which has the same vertex set, right? I just copied the vertex set from my original graph down here. So V, and then a different edge set, EST, such that, and so we'll say such that, 1, GST is a tree. GST is a tree. So what does it mean to be a tree? Well, it means that there are no cycles. There's a couple different ways of writing this down, writing down what a tree means. One way of saying a tree is to say that the path between any two nodes is unique, right? There aren't two different ways of getting between any two nodes. So if you give me node A and node B, then guaranteed, if you're looking at a tree, there's only one path connecting those two nodes, right? That is one way to characterize a tree. And so another way to characterize a tree is in terms of the number of vertices and edges, and we'll leverage that when we get to Kruskal's algorithm. But for now, what do we have? It's a tree. So 1, it's a tree. 2, GST is connected. And so we talked about the definition of connected last time. And what connected means is that if you give me two nodes, there exists a path in the graph connecting those two nodes. So what does this mean? There exists a path connecting or between every pair of nodes. And then 3, GST is a subgraph of G. So I'll say GST is a subgraph of G. And what does that mean? Well, it means that the edge set is a subset of the original edge set. Okay. And we stated these conditions in a slightly different form, slightly different phrasing last time, but here it is again, right? So now you have it copied into this notebook as well. So just as a couple examples, let's make sure that we know what spanning tree means. So suppose I've given you a graph that looks like this. That should work. Okay, so there's a graph. Okay, so now let's see what let's pick out some spanning trees of this graph. Okay, so there's our graph. Going to make it fairly small here. Here's our graph, and now let's think about some potential spanning trees. Okay, so here's one. Right, here's some spanning trees of, if we call this thing G. Here's some spanning trees of G. we could say the graph that looks like this. That is a spanning tree. Right? How do we know it's a spanning tree? Well, first, it's a tree, right? There are no cycles in the graph. Second, all of the edges in this graph I wrote down are edges in the original graph, so I haven't like added any new edges. And then third, it's connected. So every single thing is connected. So here's another spanning tree of that graph, right? So we could say here's the nodes. So I could write it like this. That's another spanning tree, right? Completely valid spanning tree. And I could there's many spanning trees for a given graph. Sometimes it's worth saying some things that aren't spanning trees, right? So what's an example of not a spanning tree? So those are some spanning trees. What about not spanning trees? Well, we could say, for example, this one is not a spanning tree. Why is that? Because it's not acyclic, right? It's not a tree, right? It has cycles, so it has one big cycle, not a tree, right? Remember, part of the definition of tree is that there's no cycles. So here's another one that's not a spanning tree. Okay, why is that one not a tree? Well, it's not connected. Okay, so this one is not connected. And remember, connected means that between every pair of nodes, there exists a path in the graph. Well, there's several pairs of nodes in this graph that don't have paths between them. For example, this one and this one, or several pairs of nodes that don't have paths. So those two nodes do not have a path between them. There's no way to get from one to the other, and so it's not a spanning tree. And then last, we could write down something like this. We could say, for example, same nodes, but this type of connection, right? So this is a tree. It is connected, but it is not a subgraph of our original graph. Right? This graph contains edges that don't exist in the original graph. So this is not a subgraph. So that's what spanning tree means. So the simple characterization of minimum spanning tree requires us to think about a weighted graph. Right? So now let's go from the definition of spanning tree to minimum spanning tree. Spanning tree. Right? So we're thinking about weighted graphs. So every edge in the graph has a weight. Right? So in a weighted graph, each edge has weight W. Let's say WE. So the edge E has weight WE. And so we'll define the weight of a graph, like the weight of a graph, not the weight of an edge, but the weight of a graph, as just the sum of all the edge weights in that graph. So let's define the weight of a graph. In fact, I'm going to write this as WG, right? So I've got WE as the weight of an edge, but the weight of a graph is WG of graph G as WG, defined here as the sum of all the edges in G, of the weight of that edge, right? And so then a minimum spanning tree of a graph G is a spanning tree of that graph of minimum weight, right? So all we do is we say, let's search over all the spanning trees of the graph, find one that has the smallest possible weight, and that is what we'll call a minimum spanning tree. So a minimum spanning tree of G is a spanning tree of G of minimum weight. Okay, and I hope it's clear that there are a lot of spanning trees in an arbitrary weighted graph. And so to find one of minimum weight seems like it could be really challenging. Right? It's not at all obvious just at the beginning of this problem that it's going to be easy to find a minimum spanning tree. And yet the whole claim of this lecture is that we have two efficient algorithms that do it. So let's explore those algorithms.